Hello and welcome to this section of the Calculus 1 Derivative Help Tutor. In this section we're going to continue working related rate problems. We're going to finish up this concept of related rates by working a few last problems here, just kind of give you more practice. Just remember the big picture is the process is the same as all of the other problems before. We're just giving you a lot of experience with different types of problems because that's the only way we learn this stuff. Okay, this problem says we have a boat coming into a dock. Above the land here on the dock is a pulley system, and this pulley has a string that goes over it and ties to the boat that's in the water. We're pulling on this rope, which is pulling the boat into the dock. All right. The pulley is 5 meters above the ground on the dock, and the boat is 12 meters out. So the boat is coming toward the dock at a rate of 2 meters per second. How fast is the rope being pulled in when the boat is 12 meters from the dock? So a lot of information here, but basically you're standing on the dock. There's a pulley above your head. It's 5 meters above the ground, so it's a pretty high pulley. There's a rope that goes over it and that goes down and grabs to the front of the boat. So we're pulling and the boat is inching forward. So the boat is coming in at a rate of 2 meters per second. Because of our pulling, eventually it's going to get a distance of 12 meters from the shore. Question is, how fast do we need to pull this rope at the moment when that boat is 12 meters out into the water coming in at this rate? Without calculus, this would be just a really hard problem to even visualize, much less solve. First thing is, let's draw a quick picture, as always. So what we're going to have is a little boat. So draw yourself a little boat out here. Right? It's a pathetic little boat, but there it is. Okay, and then over here is going to be, I'm going to say the dock, and then here's a pulley, and then here's me or somebody else, you know, smiley face over here. And then what we have is this rope, basically, that goes over the pulley and then down to the boat. So we're pulling it like this. Now this distance here is 5 meters. And the moment that we're really interested in is the distance from the boat to the dock, which is 12 meters. And we're also given that the boat is coming in at a velocity of 2 meters per second. So this is really all the information that's given to us. The pulley is 5 meters above the ground, where the boat is coming in at 2 meters per second. And at the moment that this guy is 12 meters out, what I'm interested in is how fast do I have to pull on this rope, really is what it is. So it's instructive, and I've told you this a few times already, to draw two different diagrams. One of them with just the numbers from the problem. The other one may be a little more analytic with some variables. So we're going to have to write some variables here so that we can take some derivatives. So here's the pulley again. Here's the dock again, like this. Here's me on the dock again. Okay, now let's draw our rope, same as before. So far really it's all the same. So we come over here, down like this. Okay. Now notice what we have. If you do this, basically you've formed kind of like a right triangle here. It's not kind of, it is a right triangle when you think about it. And the moment that I'm really interested in is given above when I'm 12 meters out, and here's the speed coming in and all of that. But in terms of labeling with variables, I'm going to call this distance x because I'm approaching the dock at 2 meters per second, so I'm going to call this x. And that's going to eventually translate to my velocity coming in as dx dt is 2 meters per second. I'm going to call the slant distance r, and I'm going to label this just with a number 5. There's no reason to put y here because it never changes. Really, the only reason you put a variable down is if it changes. So this guy is going to change as the boat gets closer. This distance r is going to change as the boat gets closer, but this distance is vertical distance. The pulley is fixed above the ground. It never changes. Now everything going on over here really is irrelevant for the purpose of this problem. If I'm standing here, or if I'm standing here, or if I'm standing here, the angle and all that doesn't really much matter. I'm just pulling the rope in, basically, is what the point of this problem is. So now that we know this information, let's write down what we are given. We're given, using these variables here, that, since this is x, that dx dt is equal to 2 meters per second. So that's given to us. We're also given that we seek dr dt, which is how fast I'm pulling the string. So you have to translate that from the problem. How fast is the rope being pulled when? So that's, we seek dr dt. How fast is this rope being pulled when? I should say. x is equal to 12 meters. That's translated directly from the problem. At 12 meters, how fast am I pulling on this guy? So we've really translated all of the rates and all of those guys straight away from the problem. Now the next step is, what equation can we write to relate all of these things together so we can take a derivative and put it all in here? Well, you immediately look at this and you say, well, I've got a right triangle. So I'm going to start with the Pythagorean theorem. And that's a pretty good bet because this number is fixed. This is x, this is r. So if I do a Pythagorean theorem, I'm going to involve dx dt and dr dt, which is what I either have or what I'm solving for. So that's a pretty good bet that that's what you want to do. So let's write a Pythagorean theorem here. X squared plus 5 squared is equal to r squared. All right. So just to say the obvious, x squared plus 25 is equal to r squared. Now the whole point of writing an equation is so that you can take a derivative of that equation that involves the variables that you have. So we take a derivative of this guy with respect to time on both sides. Here you're going to get 2x dx dt. We've talked about how to take these implicit derivatives enough now where you should see you're taking the derivative and then you multiply by dx dt because you don't know how x changes with respect to time. Plus, the derivative of this guy is going to be 0, so we just leave it as a 0. And on the right-hand side, you're going to have 2r times dr dt. All right, so that's kind of nice that you get a kind of a middle term drop out here. So this 2 completely disappears with this 2. And ultimately what you're going to have here is x times dx dt is equal to r times dr dt. Okay, so I'm running out of room on this board, so let me go up here and just rewrite what we just wrote. Nothing new here. So we have x times dx dt is equal to r times dr dt. Now at this point, you've identified your equation, you've taken your derivative, you're ready to solve for what you're trying to solve for, and now we have to go and look and see if we have everything we need to do that. So we go and we look and we say, all right, dx dt is given to us, so we know this. Dr dt is what we're trying to find. That's given to us. X is 12 meters. That's given to us. So we have everything that we really need, except we don't know what r is. R is this distance here, but it's the distance at the moment we care about. It's the distance when x is 12 meters. What is this distance r? That's what we need to find. And we have enough information to do that because this is a right triangle. So basically we need to go to the side here and say, in this case we'll say 12 squared plus 5 squared is equal to r squared. Make sure you know what we're doing. We're looking at the moment in time when we care about. When x is 12 meters, what is r? So it's 12 meters squared plus 5 squared is equal to this slant distance r squared. So 12 is 144, 12 squared is 144 plus 25 is equal to r squared. And so r squared is going to be equal to 169. And so r is going to be equal to 13 when you take the square root. So this rope at this exact moment that we care about is 13 meters in length from the pulley to the boat at the moment that we care about. So we actually have enough information to go and put it in here. At the moment we care about, x is 12 meters. That's the distance the boat is away. Dx dt is given to us by 2 meters per second. That's how fast the boat's coming in. Is equal to r, we just calculated at that moment, was 13 meters. And I'm trying to find dr dt, which is how fast the rope is being pulled in. So what I'm going to have here is 24 is equal to 13 dr dt. And so then dr dt is equal to 24 over 13. And this is a fraction. It's an answer. You could get a decimal if you wanted to. But it's dr dt. What distance are we talking about? We're talking about meters. In the time, we're talking about seconds. So dr dt is meters per second. So at the moment that the boat is 12 meters out, then given everything that we have, that it's coming in with this speed, we must pull on this rope at that exact moment with this speed, this 24 over 13, whatever that comes out to in terms of a decimal, meters per second. That's what we have to be pulling on to make the rope pull in fast enough to make the boat do what it's trying to do. Now, if you notice, almost all the time when I have a slanted distance like this, I label it r, x, and y. And you might be you might take some advice from that and do that yourself. So that anytime slanted distances come in, you call them r. and x is horizontal and y is vertical. That's going to help you keep track of your right triangles and help you keep your variables in your head. You can do anything you want. You could call this, you know, alpha, and you can call this beta. You know, that's fine. But if you use a consistent set of variables, it's going to help your brain keep track of what you're trying to do. So basically, that's all we did. We wrote the equation, which in this case is just a Pythagorean theorem. We took the derivative. We realized that we did not know r. That was not given to us, but we could find r, so we put it in there, and we used it to calculate the final answer that we wanted. But the process for all these is exactly the same. Draw a picture, write an equation, take a derivative, plug stuff in, get the answer. There's just some stumbling blocks along the way a lot of times. Okay, this is an excellent example of you have to read the problem, and really with related rates, you have to read the problem and translate it to math. That's the real challenge with these. So here we go. A kite is 100 meters above the ground, and it's being blown parallel to the ground away from you at 10 meters per second. What rate must the string be let out to maintain this arrangement at the moment when 200 meters of string has already been let out? Now, the nice thing about this is all of us have flown kites. So you have some idea of what they're talking about here. You've got a tight string because you've got a kite flying in the air, and the wind is blowing it, and it tells you the kite is actually 100 meters above the ground. That's the vertical distance from the ground to the height. But you know, when you're out flying a kite, the string is always slanted away from you because the wind is blowing it, right? So in this case, the wind is blowing the kite away from you parallel to the ground. That's just telling you the wind's not blowing down or up. It's blowing the kite straight away from you. And it's blowing it at a certain rate, 10 meters per second. So what we're trying to find out here is, if we're blowing the guy this way, then if we just hold everything rigid, then the kite's going to stay there. But it's telling us that we're trying to let the string out of our reel to maintain this arrangement. That means to allow the wind to push the kite along this way and take this slack out of my string and maintain the geometry of what we're describing in this problem. How fast do we need to let the string out? That's really what we're trying to figure out. So let's go ahead and draw a picture and you know, label it with some variables and so on. So here we have me or somebody, right? Here's the ground. And we have this distance here, and then up here at the top we have a kite of some kind, like this, right? And we're told that the distance, this kite, like this, the distance above the ground is 100 meters. All right? Now, we're also told that the exact moment that I care about is when I've just let out 200 meters of string. So that's basically code that tells you, okay, you got 200 meters horizontal, slanted, and I've got 100 meters vertical. That's what you have to read into that. We also know that the kite is moving along at a certain rate, so we can write that. The wind is blowing it at 10 meters per second. So what's going to basically happen is the wind's going to push the height this way. I'm going to let the string out so that I can maintain this arrangement at 100 meters above the ground and let the kite just kind of sail on this way. How fast do I need to let that string out? So let's go and draw another picture just to kind of keep it clear. Let me take this away like this. And so what we'll have is like this. So there's a kite up here. Let's call this distance x, just because we've always been doing that. This distance is really y, but we're just going to continue to label it 100 because it doesn't change. You see, that's what we say when we say it maintains this arrangement. It means stays 100 meters above the ground. The wind carries it off that way, and I'm reeling out my string so that it still maintains the same height above the ground, but the wind is just pushing it over to the right. All right, now this distance here, I need to label it r because that is changing. As time goes on, you know, maybe a few minutes from now, whenever the wind carries it down, maybe I'm really shallow with the string. R is slanted over like this. X is really long, but I'm still 100 meters above the ground as far as the kite goes. So what I have really figured out here is that I'm given that since x is labeled as my horizontal distance, the wind is blowing it horizontally. That means that dx dt is equal to 10 meters per second. That's the horizontal distance. The rate of change of this distance as the kite moves on this way is going to be the same as the wind because the wind is pushing it. And I want to seek, I should say, dr dt when r is equal to 200 meters. The reason I'm trying to seek dr dt is because I'm trying to figure out how much rope am I reeling out or string am I unreeling from my from my spool of string, that is going to be the slanted distance that the string has gone off into the sky. So how much of that do I need to let out per unit time, right? So that's r, dr dt, when I've just let out 200 meters. So we need to try to find an equation that governs all this. And again, we're given a right triangle. So we're basically going to use the right triangle. Again, a lot of these problems you will. So go ahead and say right triangle, x squared plus y squared, which in this case is 100 squared, is equal to r squared. Now again, if you put y here, it's kind of pointless because y never changes, so there's no reason to deal with it. Now the next thing I need to do is take the derivative, because if I take the derivative of this just sort of like a sanity check, I'm going to get a dx dt somewhere, I'm going to get a dr dt somewhere. Both of those I have already in my problem labeled, so I know I'm on the right track. So take the derivative of this, I'll have 2x dx dt, right? That's just taking the derivative of this term, 2x times the derivative of the inside variable, plus, this is just 0, take a derivative of a constant, is equal to 2r dr dt. Take the derivative of this times dr dt. How does r change? So when I do that, the 2 is going to cancel with the 2. And so what I'm actually going to have is x times dx dt is equal to r times dr dt. Now at this point, I step back and I look and I say, well, do I have everything I need to actually plug into here? Well, dx dt is given by 10, so I know this. R is 200 meters, so I know this. dr dt is what I'm trying to find, so that's okay to have in there. The only thing I really don't know is I don't know what x is. What is this distance, this horizontal distance at the moment of interest? So in other words, when I have let out the 200 meters, what is this distance? That's what I need to plug in here, and then I can solve the problem. But you can figure that out from what you're given. So let's come over to the side here and look at this guy here. So basically what I'm trying to say is you have a triangle here at this moment of interest. This is 100. This is what we're calling x, and this is 200. So we're going to need to solve for x right here. So let's use Pythagorean theorem. X squared plus 100 squared is equal to 200 squared. So this is the hypotenuse squared. All right? And so what you're going to have is x squared plus 100 squared is 10,000 is equal to 200 squared, so it's going to be 40,000. Okay? And then what you need to do is subtract here, so you'll have x squared is equal to 30,000. And when you take the square root of both sides and simplify it and all that, what you end up with is x is equal to 100 times the square root of 3. Right? You could get a decimal if you wanted to for this, that's fine, but in terms of a pure radical, 100 times the square root of 3. So now we're going to take this and stick it in here along with everything else. So let's do that. Let's take it and stick it right there. And what we're going to get is 100 times the square root of 3. What is dx dt? That's 10 meters per second. That's the speed of the wind. Is equal to r, which is 200, times dr dt. Like that. Now we have numbers everywhere, so we're good to go. So dr dt, which is what I'm trying to find, the rate of change of how much string I have to let out, is basically going to be equal to all the stuff on this side, so I'm going to have 100 times the square root of 3 times 10 over 200. All right, now 100 divided by 200 is basically going to be, 1/2. 100 divided by 200 is 1/2. Then you've got that multiplied by 10, so that's going to be 5. So you'll have 5 times the square root of 3. That's the answer. That's all you got. So if you really do this, you can do it many different ways. You can do 100 times 10 gives you 1,000. Divided by 200 is going to give you 5. So 5 times the square root of 3. What units do I have? Well, I have meters per second. So this is a velocity also, and so this is going to be meters per second. And this is the answer. 5 times the square root of 3 meters per second. It's one of those things that you'll start. I'm hoping to do enough of these things where you see a pattern. Hopefully by now you're kind of like, oh, I kind of see what to do. And it takes time, but after you see enough of them, you realize, okay, I'm going to draw a picture, I'm going to write some variables, I'm going to take a derivative, I'm going to see if I have everything I need, and if I don't, I'm going to go figure out the other thing that I need, and I'm going to put it in there, and I'm going to get the answer. But it does take time. This kind of thing does not come easy. Okay, this is going to be our final problem, and it's another problem that's going to seem a little bit similar to you, a slight twist there, but it's basically the same thing we've been doing. So we have a rocket going up in the sky. When a rocket is 2 kilometers high, it is moving vertically at 300 kilometers per hour. At this time, how fast is the angle of elevation increasing as seen by someone who is 5 kilometers from the launch pad? 5 kilometers from the launch pad. So we're going to draw a picture, but basically you can think about it. You're an observer. You've got binoculars. Launch pad is 5 kilometers that way. It's on the ground. This rocket goes up in the sky, and you can see you're tracking it vertically as it goes up in the sky. And so what basically we're saying is that when we get to 2 kilometers high off the ground, the rocket is 2 kilometers off the ground, it's going at a velocity of 300 kilometers per hour. The question is, how fast is the angle of elevation increasing? That should be your clue, what you're trying to find. This is the angle of elevation. Here, before it launches, it's 0, 10 degrees, 20 degrees, 30 degrees, 45 degrees, and so on as it goes up and up in the sky. So how fast is that angle changing? D theta dt. That's what we're going to ultimately be trying to find. So whatever we do, we have to involve theta because we're trying to find d theta dt, which is how fast that angle is changing. So let's draw a picture. So what we have here is an observer, right? And here we go. Here's a slant distance right here. And let me try to draw a rocket here. Okay, and here we go. So basically what we are given is that you are 5 kilometers away, like this. There is some angle, right? Obviously, as the rocket continues to increase, the angle increases as the rocket goes higher in the sky. The point of interest that I care about is when the rocket is 2 kilometers in the air, and the velocity of that rocket going straight up is 300 kilometers per hour. All right? So basically, instead of drawing another picture here, I'm just going to sort of, we've done enough of these things. I'm going to call this the x direction, and I'm going to call this the y direction. That should hopefully not surprise you, right? Now I could label this r, but what you're going to find out is you don't need it, so there's really no point to label it. But what we do know is that the next thing we need to do is write down what we know and write down what we're trying to find. So because we're given the speed of this rocket, then what basically we know is that dy dt is equal to 300 kilometers per hour. All right, that's something we know because it's this rocket's going straight up. That's the speed. All right, we seek d theta dt when y is equal to 2 kilometers. So you see it's the same form. We're given something, we're seeking something when something else is going on. If you look back through all these problems, they're almost all the same. They're set up this way. It's just you have to read it, pull that out, label some variables. There's a lot of thought that goes behind it. But basically they're all sort of set up in a similar manner. Okay? So that's what we're trying to find. Now your goal at this point is to find an equation that's going to relate these things together. Now your first thought might be, well, I'm going to use Pythagorean theorem. I'm going to have x squared plus y squared is equal to r squared. And I'm not going to say that you might not be able to solve the problem that way, but the immediate problem that comes to my mind is that if you do that, you're not going to have theta anywhere, at least not initially, so without doing something else. So whatever equation you pick, you really want to involve theta and you want to involve y because you want to, when you take a derivative, have the derivative of those two things in your equation that you have so you can use the information that you have. So you have to do something like that. So you need to start thinking of trig functions. And believe me, I know when you're doing a problem like this, you don't want to think about sine and cosine and tangent, but sometimes you just have to do it. If you're looking at a rate of change of an angle, you have to use the trig functions, almost always. So I submit to you, there's many ways to do it, but I submit to you that a good equation to use would be tangent of theta, this angle theta, is equal to opposite over adjacent. That's the definition of the tangent. So which would be y over 5. Now you might look and say, well, why did he choose that? Why did he say tangent of theta is equal to 2 over 5? Why didn't he do that? Well, that's true. The angle, that would be locking down this angle at the moment of interest, which is exactly when I'm 2 kilometers in the air. I don't really want to write that specific of an equation. I want to write a more broad equation. But I know that whatever distance I go high, the horizontal distance is never, ever, ever going to change. The 5 kilometers never changes. The angle is what changes, and y is what changes. So that's why I'm writing it this way. The tangent of whatever angle I have, no matter if the rocket's up here and I'm looking up higher or if I'm looking more shallow, the tangent of that angle is always going to be equal to how high it is in the sky divided by 5. That's the equation I want to write. All right? And so I want to go ahead and take the derivative of this. And before I do it, I'm going to move the 5 over here. 5 times the tangent of theta is equal to y. And that's just personal preference more than anything. Now I can take the derivative of both sides with respect to time. So the 5 is going to stay out. The derivative of tangent is secant squared theta. So derivative of tangent secant squared. But I can't stop there. I have to say d theta dt. Because I don't know how d theta, theta changes with respect to time. Is equal to, the derivative of this is just dy dt. Now I'll look at this equation and I'm feeling pretty good about myself because dy dt is the vertical speed of the rocket. I'm given that. D theta dt is what I'm trying to find, so I'm feeling pretty good about that. The only thing that's a little bit weird is I don't know what secant squared of theta is. I don't know what, I don't want to, first of all, I don't want to deal with secants unless I really have to. And second of all, I don't know what theta is, but I do know enough information to figure that stuff out. So first, let me remind you, the trig functions, sine, cosine, tangent, cotangent, secant, cosecant. So the secant function kind of goes with the cosine function. It's 1 over the cosine function. This is sort of personal preference, but I'm teaching you how to do these problems in the way I would do them. So the way I would write this is 5 times 1 over cosine theta squared, because it's squared, d theta dt is equal to dy dt. Because I just don't like looking at secants, to be truthful. Because ultimately I need to figure out, ultimately this is okay to have, I'm trying to find this, I'm given this is a number, all I have to do is figure out what cosine of theta is, and then I have the entire problem solved for it. And I don't like thinking in terms of secants. So let me go up to my drawing over here and see if there's a way I can find cosine of this angle. So what I'm going to do is, there's many ways to do this, okay? There's many ways to find the cosine of this angle. The first way, the first thing that you might be inclined to do is, since I don't know what the hypotenuse is, I can figure out what the tangent is. In this case, tangent of theta is equal to opposite over adjacent, 2/5. So your first thought is, okay, write a tangent, figure out what the angle theta is, and then take the cosine of that angle in here and then plug it in. That's fine, it's just that the inverse tangent of 2/5 is kind of ugly. So this is kind of, it's correct, it's just not a very nice way to handle it. Let me show you this. If you go through at this moment and find r, then you can use that to find the cosine. So there's many, many ways to do what we're trying to do, but let's go ahead and do this Pythagorean theorem. So 5 squared plus 2 squared is equal to r squared. What is the radius, or the slant height at that moment? So I have 25 plus 4 is equal to r squared. So 29 is equal to r squared. So r is equal to the square root of 29. Okay, so I found what r is. Now why do I care about that? Because ultimately, if I want to find the cosine of this angle, the cosine of theta can be defined by adjacent over hypotenuse. Adjacent is now 5. Hypotenuse is r, which is square root of 29. Okay? So I know what the cosine theta is. I don't even have to know what theta is. I just need to know what the cosine of it is, so I can take that and put it in there. So I'm ready to rock and roll. So I have 5 times 1 over cosine theta is given by 5 over square root 29. That's squared. D theta dt is equal to dy dt. Okay? And then basically, just to kind of flip this over, I've got 1 over this fraction, let me flip it over. I'm going to have 5, and then on the inside, let me flip it over and square it. So on the top, I'll have a 29, and on the bottom, I'll have a 25. Because I flip it over, and then this guy squared gives me this, 5 squared gives me 25. And then I'll have d theta dt is equal to dy dt. Okay? And then ultimately, this 5 can cancel with this, just leaving me with 5. And so basically what I'll have is 29 over 5 is equal to d theta I should say multiplied by d theta dt. Now let me plug in for dy dt. I never did that. That's 300 kilometers, 300 kilometers per hour. So it's going to be 300. So going over here for the final answer, d theta dt is equal to 300 times 5 divided by 29. So I multiply by the 5, divide by the 29. So the final answer is d theta dt is equal to 1500 over 29. Now what units do I have? This is a unit of angle per unit of time. So when I'm dealing with the pure trigonometric functions like that, the angles are always going to be in terms of radians. The time, since I had kilometers per hour, the time unit is hours. So it's radians per hour. So you're just using the units that you've been using all along. 1500 over 29 radians per hour. And that is the whole problem. There is a lot of thought that goes behind it. And you see how you have to pause sometimes and go find something else. But ultimately the same thing's going on. I've got a triangle. I know that I'm 2 kilometers in the air, 5 kilometers away. I've got my vertical speed. So that's 300 kilometers per hour. That's what that means, kilometers per hour. I'm seeking d theta dt when y is equal to this. So I write an equation. I want to involve theta and y. So tangent's the natural thing. The tangent of whatever angle I have is equal to y over the adjacent guy. I take the derivative, I get secant squared. I don't like dealing with secant, so I convert it back to cosine. And I'm ready to rock and roll. I know what this is. I'm seeking this, but I just don't know what this angle is. Now, in a calculator, you can just go and figure this angle out by taking the inverse tangent of 2 over 5. You get a decimal. And you can do that on your calculus test. It's just they don't usually want you to deal with decimals. They want you to deal with pure numbers. So my first thought was to find the angle was to take the inverse tangent, or tangent theta is 2/5, take the inverse. But if you try to do this by hand, it gets a little bit ugly. So instead of going that direction, the way I worked it is I said, well, let me go find what this radius r is. So 5 squared plus 2 squared is r squared. R turned out to be this number. The reason I did that, because then I could directly say that cosine of theta was adjacent over hypotenuse. Adjacent over hypotenuse. So I didn't have to really even find a messy decimal term, in terms of this angle. I found its cosine directly. Put it back in here, and then the rest of it's just math. Plug in for dy dt, everything's in terms of a number, d theta dt comes out to 1500 over 29 radians per hour. And that's it. And that's going to conclude our section on related rates. We've done a lot of problems on related rates. I spent a lot of time on related rates. The reason is because most students have problems with them. And they're definitely going to be on your exams and your quizzes and your homework. And the reason that most students have problems with them is because you have to read the problem, then you have to label your own variables most of the time, then you have to take your own derivatives, which a lot of times involves implicit differentiation, which is a new skill, and then you have to plug the stuff in there to find what you need to find, but a lot of times you get to the point where you don't think you have enough information to find it, but in fact you do. So I'm hoping that by showing you these problems, you'll realize that if you just take it logically and don't do anything crazy, just kind of look at the geometry, label it just step by step by step, that you'll get down to the point where at least you'll get most credit for the problem. And hopefully you'll get to the point where you'll plug in what you know, you'll plug in what you don't know, and you'll be able to solve for the unknown. So I'm Jason with MathTutorDVD.com. I hope you've learned something here. Work these problems. Make sure you know how to do them. Work some extra problems from whatever textbook you're using. Related rates can be challenging at first, but hopefully after seeing enough of these problems, they'll become methodical and something that you can get used to doing, and so that you get used to the step-by-step nature of it, and then you'll do very well in your exams and on your homework and on your quizzes.